Hello, I'm Sean Wasserman, Simulation Editor of Engineering.com. Welcome to the webinar, Digital Twin, Manufacturing Excellence Through Virtual Factory Replication. On the line with me is Dr. Michael Grieves, author and lecturer on engineering, manufacturing, and PLM. Also on the line is Fred Thomas, the Worldwide Industry Marketing Director for DELMIA, Dassault Systems. If you have any questions for them, please ask them in the chat, and we'll get to them during the Q&A. Fred, Mike, the floor is yours.
That's great. Thank you, Sean. Today we're talking with Dr. Michael Grieves on his recently published white paper titled The Digital Twin, Manufacturing Excellence Through Virtual Factory Replication. Dr. Grieves has written and lectured extensively on product lifecycle management and is a frequent keynote speaker at international conferences. Dr. Grieves' works include the seminal piece on PLM titled Product Lifecycle Management, Driving the Next Generation of Lean Thinking, in his most recent book titled Virtually Perfect, Driving Innovative and Lean Products Through Product Lifecycle Management. Dr. Grieves consults with a number of leading international manufacturers and government organizations, including NASA. And Dr. Grieves is the co-director of the Center for Lifecycle and Innovation Management at the Florida Institute of Technology, where he's also a research professor in the College of Business and College of Engineering. So welcome to our broadcast. Let's get started. Dr. Grieves, I recently saw that you were appointed head of the Center for Advanced Manufacturing and Innovation at the Florida Institute of Technology. Does that tie in with what we're going to talk about today?
Yeah, thanks, Fred. So as if I didn't need another job, but I am now the executive director of our new Center for Advanced Manufacturing and Innovative Design at Florida Tech. And our focus is to talk about and do a couple things in terms of advancing our students' education and applying their engineering studies to creating product and actually manufacturing product and supporting product, and also doing research on how do we basically do 21st manufacturing in order to bring manufacturing back to the U.S. So our focus is on this virtual to physical manufacturing that we're talking about here today, and so this does feed quite well into what we're going to be talking about in terms of factory replication.
Great. So let's get into it. What exactly is the digital twin model?
So the digital twin model is basically the idea that says, in the past, if you wanted to have information about a physical product, be it an automobile or an airplane or a rocket ship or even a mundane thing like a coffee cup, you had to be in possession of it in order to have information about it. You basically had to, so if I wanted to know how many hours were on an airplane engine, I would basically have to go track down that airplane wherever it was in the world and do a readout of what that information was. What we've been able to do since the evolution of computers and communications is basically be able to strip that information away from the physical product and create a virtual image of that, which we call the digital twin, that basically allows us to not have to go track down that airplane, but that airplane is communicating on a constant or semi-constant basis all the information we need to know about it. And so this has allowed us to do the creation of virtual products. And in the past, while we could get some information, we now can have sort of the robust information that we couldn't in the past. So if you wanted the geometry of that product, you were relegated to two-dimensional blueprints. And now when the computer revolution came about, especially in terms of being able to create digital images of products, we have very, very rich representations of that product. In fact, one of the things that I talk about in my early book was the ability to differentiate between a picture of the virtual product and a picture of the physical product, and now we're reaching the point where you really can't tell the difference. So there's been this dramatic increase in virtual product richness and fidelity. And it's not simply at the product creation stage. What the whole idea behind the digital twin is to be able to not only link the physical product with the virtual product, but keep them linked throughout their entire life. And so what that allows us to do is to basically, as we manufacture a physical product, we capture exactly what that product looks like, exactly what parts and pieces went into it, and then what we want to do is throughout the life of that product be able to as the product changes, to reflect those changes in our virtual twin. And that gives us the ability to then use that virtual twin for all kinds of different things that we would have to track down the physical product. You know, one of the things that has helped this is we're talking about a lot of data, and there's sort of two things that are going on. One is the creation of lightweight models, so we don't have to carry around as much information as we have in the past. But even that's going to go away as we basically increase our amount of computing power, bandwidth, and storage. And so while availability of lightweight models have allowed us to move down this path, we basically are because we're riding down Moore's law, which says that the amount of, well, technically the transistors on a chip double every 18 months. It means that we're basically doubling our computing power, but not only computing power, but also communications and storage. And so that's helping us out also. The last thing is that we're getting a corresponding increase in physical product digital factory floor data. So in the past, we'd go out to the factory floor and you had paper travelers, and there was really no ability to understand, you know, other than when the product finally came out and being able to do what's called quality control on it to see how it measured up. We are now being able to put sensors on all kinds of equipment, if not all the equipment, on a factory floor, and start to then basically get the data of what's actually happening on the factory in real time. And so the digital twin evolution has basically allowed us that capability.
Okay, let me just follow up on that. So if I understood you correctly, really a robust manufacturing operation management solution like DELMIA's Apriso solution plays a critical role in bringing the digital twin model to life.
Yeah, so if we you know, I'm always a big believer that we ought to visualize what we're talking about, and so this is the example of the digital twin model. Those of you familiar with my book probably saw a much reduced picture of it, but since this was done by NASA, who has the ability to do some nice graphics, this came out of a paper that we did at NASA. But basically, the main characteristics that we have with the digital twin model are sort of threefold. We have physical space with physical items, and in this case, I've got a bunch of a rocket ship, a jet engine, or a rocket engine, a rocket with boosters, and then the top of the rocket, and those physical things have always existed and will continue to exist because we live in a physical world. I talked a little bit before about virtual space, and if we sort of go over and look at the virtual space, it has all the information about those physical things from the left side. And so the key there is we basically build rich representations. Now, if you stop and think about it, the virtual space comes first before the physical space because we do design plans about these things before we build them. But when we start to talk about manufacturing, we start to build the physical elements on the left-hand side, and what we want to do is to reflect on the right-hand side the data that says exactly how those things came about. So while we may say, look at the specification of this part is X plus or minus Y, when we actually make the thing, we don't have X plus or minus Y. We have a physical number of what that specification is. And so we need to capture that information in the manufacturing process so that we know exactly what's been built. So I divide the digital twin into a couple different categories. One is the digital twin prototype, which is what we design the product to be, in which we think all the ideal products should look like. But then when we actually start to manufacture these products, we get the digital twin instance, which is basically matched up with each physical product that we make. And so if you see the two things in the middle, we have data coming over from the manufacturing side, and then when we want to have information about how that product was made, we basically have information, we use that information in the physical world to make quality decisions. So the manufacturing piece is about building these digital twin instances and being able to understand exactly what has happened out on the manufacturing floor.
Okay, great. When I look at it, though, it's not so much that the digital twin provides an answer, but it gives you really more in-depth information to make choices and decisions. Would that be right?
Well, that's exactly right, and I think the problem is that we really don't have a great feel for what information has allowed us to do. And so I sort of created this graphics that said, what information is a trade-off of time, energy, and material. And what I mean by that is if you look at the left side, you can take any task, manufacturing a rocket ship, designing a new airplane, or the example I like to use, which everybody can understand, is putting together a new bike at Christmas for the kids. And so if I take any particular task, I can divide it into two parts. One is the minimum use of resources that it would take to do that task if I was omniscient and omnipotent, meaning I knew everything and I could do everything very well. And then everything above that, so that's the green area on this chart, and everything above that is the red area is information inefficiencies. So I don't know, what exactly my rocket ship propulsion is going to do. So I have to do a lot of trial and error to figure out whether it's actually going to lift the amount of weight that I want to lift, or I don't know how long my wings of my airplane should be and what my lift is going to be under those wings, so I basically do experimentations, or I don't know where the wings are going to break, so I have to basically do work there. So if I take any of these tasks, I can, in our world, cost them, because I can cost time, energy, and material. And so that's sort of the world that we live in. What humans can do is they have this thing called information that basically is a replacement, not for the amount of physical activity I have to do that would require me to do the task at hand, but it does trade off for the information inefficiencies. And in this particular graph, I show it trading off completely, but the reality of it is that never happens. But it gives you the idea that says if I can create information, I can know not to do this particular design because it doesn't work. I can know where I'm running out of inventory at a machine level so that it doesn't sit there idle. So it allows me to basically trade off information for these information inefficiencies. The problem is it's really tough to cost information. But what makes this all work is the formula that basically is there for the math geeks, that basically says if over all the different tasks the cost of information is less than the cost of wasting resources, then I can trade off information for that. And in fact, that's what Fred, your company Apriso, tries to do with respect to collecting information, so I can make good decisions and not do wasteful, inefficient, and even stupid things out on the factory floor. So I don't think we really have a good appreciation for what information can do for us, but clearly we see the benefits of it every day, and so I will contend that the reason we've done so well in the last 25 to 50 years is information technology has come along to allow us to not waste resources the way we have done in the past.
Excellent. Really, really good insight, Mike. You talked to many different manufacturers around the world. I know you're, consult with them on a regular basis. So, in your opinion, where are manufacturers today in relationship to the potential of the digital twin model to help them take their manufacturing, really to take their product processes to the next level.
Yeah, so you know, I'm optimistic about kind of where we're going, but kind of the reality of it is that today a lot of the work that we do is sequential and independent. We basically, you know, have very different organizations that develop and even engineer the product, and then the organization that is tasked with manufacturing the product is a completely different organization that really doesn't share much information with those. I won't even talk in today's webinar about the poor people in the support sustainment phase who really get the short end of the stick with respect to the people at the front end not taking into consideration the support and sustainment issues of products. But even between engineering and manufacturing, there's this huge gap that basically says that we do sequential work and independent work, and then we hope it comes together. So we do develop, you know, a 3D model and an engineering bill of material, and we think that that's, you know, how we are going to build our product. But the manufacturing people then have to develop a bill of process, which is the recipe. Some people use different terminology. I call it a bill of process. But this is the recipe that says, here are the steps and the activities that have to occur to take raw material coming in the back door and producing a finished product out the front door. And so the bill of product is the development process, but they even develop their own manufacturing bill of materials. And a classical problem that is still at the forefront of a lot of organizations is this EBOM to MBOM inconsistencies. So what happens is that the engineering people and even the engineering manufacturing people take their designs and in the past they've been blueprints, but even 3D models, and they throw it over the wall to manufacturing. And so I always kind of compare it to a relay race where engineering is running down the track and hands it off to manufacturing, who is supposed to then run to the finish line. But the reality of it is that in most organizations, what it would look like is engineering handing it to manufacturing, manufacturing running a little bit of ways, turning around, running back to engineering, and having engineering backtrack. And so you have this back and forth thing that is hardly conducive to a relay race, let alone to manufacturing. And so they throw these designs over the wall to manufacturing, only to have manufacturing not to be able to build it or have problems. I mean, the other core issue, in fact, we're wrestling this one at NASA, is a lot of times manufacturing might have a better way of doing things that would change the design, make the design even better. So, for example, we have to use a more expensive material when manufacturing can say, look, if I put in a couple of these stress areas, I could basically use a lighter weight material. So we really haven't done a very good job overall in terms of connecting the two. And then often we develop 2D blueprints for manufacturing floor when we've been working with 3D models. Now, some of the more progressive organizations, you know, are now putting 3D models on the factory floor, but there's still a fair amount of 2D blueprints. And one of the problems with today's generation is there's very few people who have the ability to take a 2D blueprint and visualize a 3D model. That is a rare kind of capability in today's world, and some of the old line manufacturers could do it, but we're running into problems with the newer generation not having that capability.
So this is really about closing the loop, if you will, and creating that continuous loop of improvement between the engineering community and the manufacturing community, and this becomes an advancement, if you will, in making that happen.
Yeah, well, and so the issue that we're talking about here today is the fact that we have spent a lot of money in doing modeling and simulation for factory operations, only to discard those once it goes out on the factory floor, and we find out that the build process is very different than what it was proposed to be. And so So what we're talking about here is basically being able to reuse these factory simulations that are really quite good. In fact, there are a number of instances that I'm aware of where you can save tremendous money in being able to simulate what happens on the factory floor before you actually build the factory. At NASA, we saved millions of dollars and because we build our own machinery, and we found out that we had a piece of machinery that wouldn't reach into where we needed to reach in stir welding, and in the past that would have cost us millions of dollars in 6 to 9 months in retrofit, and we found that out by doing simulation. But now that we've had that build that, the whole idea is to say, well, let's use that simulation to talk about what's actually happening on the factory floor. But in order to do that, if you remember back to my model, I'll see if I can do this, is that we really need to basically connect the physical model with the virtual model. And so what's missing in to be able to do that is we need a unified repository that basically allows us to have both the physical and the virtual connected. And then what we need to do is have 3D location and characteristic tags that are on the factory floor that's basically looking at actually what is happening on the factory and being able to feed that into our simulation so that we're not simulating anymore, we're basically reflecting what's occurring on the factory floor. And so we're basically looking at manufacturing execution system tags that would basically allow us to know what the placemaker of what it is that we have designed in, so we're collecting the right information to match up against the replication. So this leads to the concept that we're talking about today, which is digital factory replication. So all we're talking about here, although it's non-trivial from actually doing this, is the ability to take the simulations that we spent a lot of money on and then keep running them as we're running the factory and see exactly what's happening on the factory floor versus what we have predicted to happen. And the whole idea of that is being able to then be able to see, no matter where we are, because of this idea of virtualization, we would have access into what's happening on the factory without having to be on the factory floor at all. So I think that what this does is take the digital twin to the next level that allows us to basically be able to match up what we thought was going to happen with our products and how we were going to build them with what's actually happening with our products and how we're actually building them.
You know, I can see this impacting a whole host of metrics that most manufacturers, value today, from quality to time to volume to time to global volume. It just accelerates the entire process in that relationship and has the potential to impact continuous improvement programs on an ongoing basis.
Sure. So if you sort of look at the example that we have out here, we're looking at a screenshot from a factory simulation, and what we're saying is so you see if you've ever seen the factory simulation, they're pretty cool because you can see the actual units moving on, and you can zero in into the actual cells. And in this particular case, not only are we actually seeing the simulation, but in factory replication, if you look at sort of the balloons that we have superimposed on this, and this is just for illustrative purposes, we're basically showing what was supposed to occur and then matching that with what is actually occurring, and that allows people to zero in on the problem areas. And so we can see that if everything was green, we are at a particular station, measuring what we've produced and comparing that to what we thought we were going to produce. And if it's all green, it means that we're doing a good job. So by basically using the money that we spent in simulating it, we're taking it to the logical next step, which is saying repurposing it to basically being able to then track it as production occurs to see exactly how we're making this. And in point of fact, the only way to do this sort of today is to look at a sheaf of reports and then compare it to what we thought was supposed to be manufactured and make our decision. This gives us a nice visual representation of how it is that we should, how it is that our factory is operating, and allows us to zero in pretty quickly without either looking at a report or walking the factory floor.
So let's drill into this a little more and get into a little bit more detail on this. I think we have the time to do that. Let's go back to the model real quick. Is the concept in your mind limited to certain manufacturing models, say just lower volume, maybe high mix type, construction equipment, agricultural equipment, or can it work also in high volume environments, maybe even repetitive environments?
Well, from my perspective, I think it would work in both environments, because I mean the whole idea is in fact where it would be most useful is in high volume, where you can't afford to have products not being produced to how they're supposed to be produced, and you're basically having complex situations like this auto plant where a problem somewhere in the mix here will basically cascade into bigger problems down the line. So obviously the higher volume opportunities are there for complex products. Now, if I'm producing paper clips, I don't really care. But if I'm producing automobiles or electronics or things like that, where I'm looking at high volume, then knowing how the factory is operating can give me early warnings where I'm basically looking at that. But in slower volumes, even airplanes or a little higher volume than that, being construction equipment, being able to see all the stations on the factory floor. If I've gone to the expense of creating a simulation of it, I really don't want to put that into a drawer and basically just simply then rely on the factory. If I could repurpose that so that any executive in my organization could see what's happening out on the factory floor at any point in time, and by the way, I would collect this information so that I could do not only statistic process control, but also look for trend lines and look for where I was starting to drift off of my tolerance corridors, to be able to make good decisions about what's occurring on the factory. And so there was a reason that in factories you put the plant manager's office overlooking the factory floor with a window. This is that window, except for the fact that for the most part, the factory manager could only look at big problems, i.e., when the assembly line stopped. But this allows that factory manager or even other members of his team to look at the factory at any point in time, from home, wherever, and know exactly what's occurring in the factory that they were local to, or even halfway across the world.
It's almost like that virtual overhead office in the center of the factory.
Exactly, and that basically, again, if you go back to my premise that information is a trade-off for wasted resources, that having this information would allow us to have a better handle on where we were starting to have inefficiencies occur in our manufacturing process. I mean, I go back again, when we spent a lot of money on doing these digital simulations, boy, I could repurpose that and just continue running it as a factory replication of what's occurring if I can get the information off the factory floor, which is why I propose this unified repository.
Okay, let me ask another further question, especially with this example sitting there. And obviously I have a vested interest in this particular area, but it just seems to me that it becomes highly important for manufacturers to really think about their manufacturing shop floor, and regardless of their history, and how many spreadsheets they may have used to run the factory floor, or how many different disparate systems they have, it's never too late to start putting your strategy together to put a robust platform on the floor that for manufacturing that is truly collecting the important information that you would need to fuel a concept like digital twin.
You're right, and so there's a lot of initiatives that are going on in not only in the U.S. but across the world in terms of making all these machines be smart and being able to communicate. So, Industry 4.0 or the smart machine concepts. I mean, all these concepts are about instrumenting what's occurring on the factory floor to allow you to collect information about how manufacturing occurs. Now, some of what we're talking about is basically having machines communicate with each other to adjust for different aspects of one machine doing something versus another. But collecting that information into a virtual twin of the factory even is this opportunity to basically be able to get in front of what's occurring in the smart machine area and merge that with what has occurred, which I would consider to be pretty robust in the factory simulation. So we're really just taking it to the next logical step here, which says, we sort of need, three different things that we're talking about here. We need the simulation itself. We need the machines to have instrumentation, which we're starting to see more and more of, and then we need to be able to collect that data into a manufacturing execution system so that we can merge that information with what we basically had designed, had what our designs were, and being able to do then that visualization and comparison.
Yeah, and that in the real-time nature of this really negates continued use of your old legacy solutions and spreadsheets, and as a further reason that investment in something like DELMIA's Apriso solution becomes critically important, because real-time is the necessary time to support this concept.
Yeah, I mean, quite frankly, you still can collect the data and do analysis after the fact in spreadsheets or big data or whatever. But if you're sort of looking at spreadsheets by their very definition, you've already had the problem, and so this idea of having a visualization real time is, I think, extremely important. I mean, I basically have said, in fact, in my first book, that our highest bandwidth is our vision, and so all this does is make sort of the data visible to us in such a manner that we can start to make decisions much more quickly, and in fact with better data than we have had in the past.
Great. Let's move on. This was an area that was in your white paper that I just found fascinating, but it's the use cases and how you had laid out the use cases that support this. Could you go into that a little bit?
Sure. So I wind up with sort of the 3 C's: conceptualization, comparison, and collaboration. And what I mean by conceptualization is you mentioned spreadsheets and reams of data. As humans, we're really not really good about being able to assess, look at a spreadsheet and look at the pool of data in there and make good decisions about that. I mean, we're just not set up to do that. Computers do a much better job of being able to do that analysis. So this idea of conceptualizing, giving us a picture of what's occurring in terms that we understand instinctively, being able to view it. So if you go back and look at the balloons off the particular stations, that immediately tells us which station it is, what we were desiring, what we got, and and we can look at the trend lines along that line to determine, hey, am I looking at red from one point on, or did it just start at one station, or do I start to see drift? I mean, it allows us to make very good, very quick decisions by being able to conceptualize what we're talking about here. The comparison piece is something that we do as humans. Is the idea of what do we want and where are we actually at today? And so this idea of human nature is to basically close the gap between the ideal and the actual, and we basically are able to do that effectively if we can understand 2 things. What is it we really want to do, and where are we really at? problems that always occur in that area is we don't understand what the current situation is, so we make faulty decisions, or we don't really understand what it is we're trying to accomplish or gain, or what our outcome is, and so we basically aren't closing a gap between anything that's really important. And so comparison is what humans do instinctively, whether you're driving a car and you're comparing the person turning in the lane in front of you versus where you're at, or you're basically looking at the factory floor to basically say, here's what my manufacturing goals are, and here's where we're at. The third aspect is what humans do very well, and that's collaboration. So instead of having to send one person out on the factory floor who reports back what's going on, we're talking about factory replication is being able to see what's occurring, by many people, and then being able to bring to bear the collective knowledge to solve problems. So if there was a problem on the factory floor, rather than having to put people in airplanes and ship them to that factory, those people who we would rely on to come up with help on this can simply look at their replication and understand what's occurring on the factory floor immediately without having to travel or spend the time and effort. So this goes back to the premise that information is a replacement for wasted resources, because basically having people travel for a day or 2 days with the expense of that in order to be able to see something that they should be able to see from information that would be available to them is clearly a waste of resources. So these are the sort of the three use cases that I come up with, is this idea of conceptualization, being able to visually see the information as opposed to having to tease it out of reams and reams of reports. Comparing what I'm trying to obtain versus where I'm actually at, and closing that gap, and then finally being able to bring to bear the resources of the individuals who can collaborate on creating a solution quickly and efficiently without having to expend unnecessary resources.
Okay, we're moving toward the end of the formal presentation because we want to leave enough time for questions. In summary, realization then of the digital twin concept in a real-world environment is not only feasible, but from what I gathered from the presentation, it's really a game changer, especially when you think about all of the dramatic changes in this Internet of Things rush that is going on today.
Yeah, so the good news about where we are in our industry is, if you don't think we have enough capability, wait 18 months and it's going to double. So there are dramatic advances, in virtual product representation and the physical product digital data. I mean, if you look to even back to the beginning of this millennia, that we have made huge strides in virtual product representation. Even simply looking at the three-dimensional representations, one of the things that I had proposed in my first book was this Turing test idea that says, can we distinguish between a virtual product and a physical product on a realm of ways, and one of them is visual. And today I've seen image of a physical product and the virtual representation, and you really can't tell the difference. So there's been dramatic advances in the technology that we rely on. What's missing is the connection between the virtual product and the physical product. And so if you go back to my model, the connection, what we've done, we obviously have pretty robust physical products because we've flew to the moon and back, and we are now getting to have very robust virtual products. The connection between these two has been the thing that has not been robust enough. And so if we're talking about a factory replication, we got to be able to get the data off the factory floor to compare it with what actually was the design. So that's the area that we need to kind of keep focusing more and more on. And this connection drives instantaneous and simultaneous perceptions of manufacturing. So if I can see what's happening on the floor in real time without having to be actually there, and will argue that even if you physically are on the factory floor, if it's a big factory, things are occurring in parts of the factory that you don't have any access to because you're just not physically there. But basically, this produces a virtual set of eyes for us that allows us to see, and drill down to any part of the factory itself as to what's happening. And it can happen simultaneously with people not co-located with the factory, but anywhere in the world. And I would argue that this connection would improve productivity. So we would not waste as many resources. We trade this information off for waste resources. Uniformity of production, because what we would do is capture problems a lot earlier and not have variations in our tolerance quarters that sometimes we have today. And obviously that improves quality. Now my definition of quality is a little bit different than sort of classical manufacturing. My definition of quality is, will it do the things that the user wants it to do when he uses it? But from a classical quality control specification management, I think that it allows us to have less variation in the product if we have better information that's coming off of the factory floor that we're comparing to what it is that we're trying to improve.
Absolutely fantastic. I think the presentation, Mike, really struck a chord with me. How ultimately close we are to really taking the shop floor to the next level. I think you wanted to say one more thing with regard to Florida Tech.
Yeah. So one of the things that I think is a particular problem is this idea that understanding the connection between engineering, manufacturing, sustainment, and support. And so in order to address that, we have created a certificate program at Florida Tech in product lifecycle management, which covers these areas that we've talked about today. And so anybody who's interested so my belief is that if people have a better understanding of all the elements, we're going to do less of siloing and inefficiency between functional areas, and better job in terms of sharing information across the life cycle. And so the Florida Tech PLM certificate program is 24 modules of all this information about PLM and how it impacts and what the value is for today's organizations.
Great. Dr. Grieves, thank you. And with that, I'll turn it back over to Sean for some questions.
Perfect, thanks, and great presentation, guys. Actually, the next person to ask a question here, Grieves, was really impressed with the presentation. They say, are you saying that in the near future the tracking and genealogy of products will be shown within the 3D model, data like as designed, as built, as maintained, which will be unique to the model? Will that all be accessible through things like simulations, digital mock-ups, and the design phases? And if we're not there yet, how far are we from this?
So I'm always reluctant to predict how quickly we do things, because it seems like this technology has moved a lot faster than even I predicted it was going to do. But yes, I think the ideal, as my NASA colleague John Vickers said, is the ideal is what we would like to do is to design the product virtually, manufacture the product virtually, sustain and support the product virtually, and only when we get it all right do we basically go physically move around some atoms. So we want to trade off. We want to trade off bits for atoms, wherever we can, especially being able to get this. Now, that's the ideal and the ultimate vision. But we are seeing a whole bunch of activity occurring in terms of reaching that particular aspect of 3D models. So 3D models started off as simply geometry. We're now adding a lot of additional information, and we're using it for behavior analysis, finite element analysis, stress analysis, things like that. And so yes, I think that at some point in time, you'll be able to inspect the virtual product, and you'll be able to obtain all the characteristics that you would be able to obtain from having possession of the physical product. But I'm not going to predict the time frame.
I like how you said trading atoms for bits. I like that. So is
trading bits for atoms.
Bits for atoms. Yes. Sorry. Oops. Is there any commercial tool that currently supports the concept of the digital twin?
Well, it depends on kind of which part of the digital twin that you're looking at. So certainly today, what I call the digital twin prototype, which is the development model, that's supported in CAD. Being able to do the analysis is supported by a lot of solvers. So the realization of a physical product from a virtual product exists. We really haven't done as much as we need to do in terms of taking a manufactured product and creating a virtual twin of that, although we do collect some information. And I guess I ought to sort of caution that we may not need all the information about the physical product in the virtual product. It's going to depend on what our use cases is. So for example, I'll use a trivial one. If we don't really care what color the product is, we wouldn't have that. You wouldn't have that in the virtual twin model. So there is a cost to having information. I mean, it's not free. There always is a cost of developing that information. So you got to figure out do you have value to it? The premise that I'm talking about here in terms of factory replication, I haven't seen a representation of that, but I think other people are working on being able to make that happen. We have parts and pieces. We have very nice factory simulations, and we have information being collected off the factory floor. It's going to take my unified repository to basically be able to make a factory replication a reality.
Okay, perfect. How can the digital twin help the continual improvement of manufacturing processes around the world?
So one of the things that can occur here is while I showed kind of one factory in my slide, if you had multiple factories that were this way, you could not only see what's happening within one factory, you could basically compare factories across the globe with each other to see where one factory had inefficiencies that another factory didn't have, and then drill down to find out why that was occurring. And so this idea of continuous improvement. So what happens a lot of times with continuous improvement today, Kaizen as it's been stylized, is I really have to move actual physical things around on the factory floor in order to be able to compare these improvements. If I could simulate those improvements and then send them off to after I have validated that they would give me improvements, I could ship those off to all the factories and then tracking them, make sure that they implement it in the proper fashion. So while I show sort of one factory, in terms of collecting that data and being able to show the replication, there is no reason why you couldn't have multiple factories that you were looking at all at once and then collecting that information off of each of the factories and comparing each factory against each other in order to understand where improvements in one factory vis-a-vis another factory were available. The one thing I even haven't talked about is being able to feed that information back into the engineering design phase, so that if there were inefficiencies in the manufacturing process as designed when the product was designed to be built, you would feed that back so that the next version of the product corrected that. too often you see that the same problems are solved over and over again, as each generation of the product is rolled out. And and that's the reason is that the designers really have very little, if any, connection to the factory floor, so don't understand, what problems have occurred and why manufacturing process should be changed. And the next version of product comes along with the same design bill of process from the engineering, from the manufacturing engineers, and as a result, you wind up solving the same problem over and over again. So there's a number of reasons, why this would help. This would help in terms of doing a better job in reducing efficiencies, improving productivity on the factory floor.
Perfect. Now, what role can connected technologies like, say, the cloud or IoT play with the digital twin?
Yeah, so I'll ignore the cloud for a second, but IoT, the Internet of Things, and in fact, Florida Tech is doing a lot of work, and we're going to train our own engineers, but are creating curriculum for this particular area because it is, I think, a seminal technology. Is basically this idea of having everything be smart. And so I can't collect data. I mean, I guess I can collect it manually, but the best way to collect information is for the machines themselves to report as to what exactly is happening. And so the Internet of Things is going to, in essence, make the new machines smart and communicatable. And in point of fact, there are a number of projects out there to even retrofit older machines to collect information to feed in. So I mean, the IoT is kind of I almost call it a fuzzy concept, but it's a pretty encompassing concept. One of the elements of IoT is basically having physical products have intelligence in order to do two things: sense and communicate. So they need to sense what's happening, and they need to be able to communicate that. IoT is sometimes extended into machines talking to each other, but even then, if let's just say I have machines that are changing their program or changing their parameters in order to compensate for other things that are happening in the factory, I really need to understand what they're changing. So part of IoT is smart machines talking to each other, and so if I make a part that has a negative tolerance, the next time I put it in the machine, I want that machine to recognize it was a negative tolerance and try to make a positive tolerance. Even if that's occurring on the factory floor, I really want to know that happened, as opposed to being surprised at the end of the process. So having intelligence in machines, I think, is a good thing, but unless you have a digital twin that allows humans to know exactly what's happening, I would sort of contend that those kind of systems can go out of control pretty quickly and can cascade failures. So digital twin is important, even if I have said, okay, well, I've got my smart machines talking to each other, why do we need humans? Well, while I won't contend that it's the Terminator movies, I think you can get some really bad outcomes if you're not in control of that from a human perspective. And our virtual factory replication allows us to do that.
Okay, next question is, what benefits does the digital twin bring to CAE simulation?
Well, it's basically, you have to have it because of the fact that if you're simulating, what are you simulating? And so the idea is that you have a physical design that you either have, it's been manufactured, or in the case of the digital twin prototype, is something that you want to make. So if I'm going to do simulation, what I got to do is get the physics right of what happens in the real world in order to be able to simulate even the geometry or the behavior of my physical product. So, for example, I want to be able to. So I'll give you the trivial example. If I lengthen an iron beam, I could have a simulation that just simply allowed me to place that, let's just say that I'm building a building and I need a beam that runs a little farther, and so I add length onto that beam. Well, if the simulation doesn't add weight at the same time, I wind up with a building that really doesn't work because that beam will not hold the weight it's supposed to hold. So you got to get the physics right, and that's one of sort of the challenges that we have facing us is in simulation, being able to simulate, being able to replicate what occurs in the real world in the virtual world. Now, the gamers have it easy because they can make up their own rules about what the physics of the universe are, and that's particularly fine. So people can fly, you can have gossamer structures that support a lot of weight. That's the easy stuff. The hard part is being able to have a simulation that reflects what actually occurs in the real world. And so that's where the simulation people are really earning their money, is being able to build in the physical models that reflect it. So if I said, I want to design the product virtually and test the product virtually, the idea behind that test is that if I take that product and test it physically, it will give me the same results. So the digital twin is basically built into the concept of modeling and simulation.
Good answer. So has the virtual twin digitalization changed technical requirements or job descriptions for a traditional end user? Has it altered the hierarchy of engineering and management? For instance, if you're a classical mechanical engineer, do you need any new skills?
That's a great question, and obviously at Florida Tech, it's one that's first and foremost on our mind. And my contention is you do. I mean, I think that the days of knowing a lot about a little are if they're not gone away, they're going away quickly. And so mechanical engineers, are going to need to know more about what they're designing into in the context of design than they've had in the past, and they're going to have to be able to do modeling and simulation. In the past, the mechanical engineer would design, let's say, a structure, and then give it to the analysis people, who would days later come back and say, that ain't going to work for you. Today, there's no reason why mechanical engineers can't do a lot of their own engineering analysis as part of the systems that they have. So it is going to sort of broaden. Now, engineers are never going to go down on the manufacturing floor and manufacture products, nor vice versa. But having an understanding of what those elements are, being able to, in essence, look at the product life cycle, I think is critical in order to be able to take cost out of it. And so if we do sort of classical manufacturing where engineering designs the product and then sends it to manufacturing, who can't manufacture and sends it back to engineering, and we have all that waste of resources, we're never going to be able to take cost out of the manufacturing process or do it as efficiently as we can. So it does have implications for the student graduating who's going to have those capabilities, and hopefully as an educational institution we're going to do a good job. The second question there is an interesting one, is yeah, it should make so I'm a big believer in basically pushing the decision down to the people most capable of making that decision as opposed to hierarchical decisions. And I think that having the information and data available so that you can turn to the most knowledgeable person and say, is that thing going to do what it needs to do, as opposed to somebody from the top saying, here's how we design the product, is going to be key. So I think it does change by having people at lower levels having better information at their fingertips about what actually is occurring either in the design or manufacturing it should change our structures in our organizations. I mean, we'll still have some level of hierarchy, but as I said, the most knowledgeable ought to be making decisions about how design and manufacturing occurs.
Thank you. So I think that's all the time we have today. So again, I'd like to thank Dr. Grieves and Fred for this presentation. You guys did a really great job. And I also want to thank everyone who is here on the line with us for listening in to the presentation. I hope you all enjoyed it as much as I did. So Dr. Grieves, Fred, thank you very much.
Thank you.
Thank you.
Have a good one.